Welcome viewers to the third lecture for the online series of lectures for the course of Dynamical Systems. In the second lecture we discussed continuous dependence on initial conditions towards the end of it. In this lecture we'll start with the second version of continuous dependence on initial conditions. So continuous dependence on initial conditions. Second version that will turn out to be useful in this lecture. Okay, let I denote an open interval and big U an open subset of R to the n as usual. Suppose F is a map from I cross U to R to the n, and this map being continuous, and it also satisfies a local Lipschitz condition. A local Lipschitz condition in the second variable. Condition in the second variable at every point t comma p in I cross U. Okay. Now let us fix our initial point. Let t0 comma p0 in I cross U, and let j sub p0 denote maximal interval of existence, right? Interval of existence for the following IVP. dx over dt is equal to ft comma x. Okay, it's a time dependent vector field, and x, the solution at the initial time t0, is nothing but p0. So we number this equation as 1. Now this second version of continuous dependence on initial conditions says that for every real number t, such that this big T is greater than the initial time t0, and of course this closed interval t0 to t should be contained in the maximal interval of existence jp0. If this is the case, then there exists a positive number r of t. This r of t signifies that r depends on this big T that we started with, okay? Such that if the norm of p minus p0 is bounded by r of t, okay, in other words, or that is, if p, this point, belongs to the open ball of radius r of t centered at p0, then the solution U sub P of the IVP, this IVP, dx over dt is equal to f of t comma x, and x of t0 is now just p, no longer p0. So we are looking for a solution of this IVP with the initial condition given by this. Okay. This we number as 2. Okay. So if this is the situation, then the solution UP of this IVP exists on this interval t0 comma t, which is of course contained in jp0, j sub p0. Okay. All right. I need some space. Furthermore, the the number that we get out of this expression. So we take the norm of the difference of these two vectors upt and up0t. They are both vectors in R to the n. We take the difference of these two vectors and then take the norm of it. Okay. So by varying t in the interval t0 comma t, we will get different numbers, okay, different positive numbers. So we are going to get the maximum of those positive real numbers by varying t. Okay, that gives us the distance between these two solutions in the space of solutions. And we are now going to take the limit of this expression as p approaches to as the point p approaches the point p0. P0 was this point that was responsible for the first initial condition, and p is the point that is associated with the initial condition for the second IVP. Okay, and the limit has to be 0. Okay, so it, in other words, tells us that the distance between these two solutions can be made arbitrarily small as p approaches p0. Okay, where up0, so up0 was not, I did not mention about up0 earlier. Okay, up0 is of course a function from j sub p0 to u and is the solution to the first IVP, is the solution to the IVP1. Okay, so this is the second version of the continuous dependence on initial conditions that we'll require in this lecture. Okay. All right. So another important result that is called, which is called extensibility lemma, that we are going to state now. Okay, without any proof. So now another important result called extensibility lemma. The the name suggests that we are going to extend our solution to a somewhat larger interval, okay? So let I, as before, denote an open interval, and U, an open subset of R to the n. Okay, good. Suppose in addition that f from I cross U to R to the n is continuous and satisfies a local Lipschitz condition in the second variable. Satisfies a local Lipschitz condition in the second variable at every point t comma p in I cross U. All right. Now let T0 P0 be a point in I cross U, and A and B are two real numbers such that T0 lies between A and B, and we also demand that the interval from A to B, the closed interval from A to B, is contained in the interval I that we started with, okay? This interval. Okay. All right. So these 2 points, these two real numbers, should be chosen such that this closed interval is contained in I. Suppose that small u from the open interval from A to B to big U, the open subset of R to the n, is a solution of the IVP 1. I erased it, okay? So equation number 1, go back there in the previous slide and see that equation. So let me write it for you if you have trouble going back to the previous slide. On the side I write it for you. dx over dt is equal to f of tx, and x of t0 is just p0. Okay, this was IVP1. Okay. Good. Okay, so this is a solution of, so u from A comma B to big U is a solution of the IVP1 defined on the open interval A comma B, on the open interval A comma B. Okay. Then there exists, if this is the case, then there exists an extension of U, the solution, to a larger interval, to an interval A comma B plus delta. Okay. So we immediately see that this earlier interval is contained in this larger interval, okay, for some positive delta, and this will be the situation that the extensibility will be allowed if and only if there exists a point P in the open set U of R to the N and a sequence of numbers lying in this open interval. Okay, a sequence Tm in A comma B such that the limit of this sequence goes to B, the right end point of the interval that we started with, A comma B, as M approaches infinity, and the corresponding solution approaches that point P in U. Okay, so if and only if this condition is satisfied, we will be able to extend our solution to this larger interval A comma B plus delta for some delta, so for some positive delta. Okay, so this is what the extensibility lemma states. All right, so now earlier in lecture 2 we shed some light on flows of vector fields. Let us get back to that discussion. Here again, flows of C1 vector fields. Okay, so let me remind you about this vector field f t comma x. Okay, which means that there are actually n plus 1 independent variables in this case. One is the time variable, the other n variables are like x1, x2 all the way up to xn, representing the coordinates of R to the n, the spatial coordinates. Okay, so when I say that f is a C1 vector field, I mean that these derivatives, the partial derivatives of f with respect to t and the partial derivative of f with respect to xi, I running from 1 to n, are all they all exist and they are all continuous functions. Then I say that the underlying vector field is a C1 vector field. Okay, so now we are dealing with flows of a C1 vector field. So we consider the autonomous system. Given by dx over dt is equal to f of x, meaning that the vector field that we are considering is now a time independent vector field. It does not depend on time explicitly. Well, I should not say that time independent, because x is, it depends on time implicitly, but it does not depend on time explicitly. That's what we mean by autonomous system. Okay, the underlying vector field does not depend on time explicitly, where f from u to r to the n is a C1 vector field. Okay, so now we are considering all these functions to be continuous functions. C1 vector field on some open set u of r to the n. Okay, we know by means of fundamental theorem discussed in the previous lecture, that is the uniqueness and existence theorem of ordinary differential equations, that for each P in this open set U, there is a unique integral curve U sub P from J sub P to big U. Okay. Defined on a maximal interval of existence J sub P, and which solves the IVP dx over dt is equal to f of x. Okay, it does not depend on t explicitly anymore, and x of 0, I mean that at the point at time 0 the solution has to be equal to the point P. Okay, let us call this equation 2a. Okay, well, this is the situation because a C1 vector field F is necessarily continuous and locally Lipschitz. Okay, because when I claim that the vector field is C1, that is a much stronger condition than claiming the vector field to be continuous and locally Lipschitz. Okay, so that is the reason we have all the conditions for the fundamental theorem of of existence and uniqueness of OD is satisfied, and we have we have this thing happening. Okay, now we can therefore define a map. Define a map theta from calligraphic D to big U on a subset D of R cross U given by, so this is the domain of the map theta. It's the collection of all ordered pairs T comma P in R cross U such that T belongs to the maximal interval of existence. Okay, this is what we call equation number 3. Okay, and this map theta on this domain T is defined by this way. Theta of T comma P is nothing but UP of T. Okay, UP is this unique solution of the IVP. Okay, so for all T and T comma P in the domain D, calligraphic D, this is equation number 4. Okay. Okay. I need some room here. Let me erase this part. We'll state that the domain of theta D, the domain of the flow map theta, that is D, given in equation number 3, is an open subset, is an open subset of R cross U. Okay, so this is the first thing to state and prove. Next, we'll state that theta is also continuous. The flow map is continuous. Next, we'll state and prove that the flow map theta is continuous. Okay, these are two important results to be stated and proved. We'll then discuss some fundamental properties, of theta. Okay, so these are the plans. Okay, the set D, the domain of the flow map, the set D is called the flow domain. The flow domain. Okay, of the vector field F, of the vector field F, and theta is called the flow of the vector field F. Theta is called the flow of F. Okay, good. Flow domains and flow maps. So now we define flow domains and flow maps in detail. F from U to R to the N will denote a C1 vector field, which is of course continuous and locally Lipschitz. C1 denote a C1 vector field. Defined in an open set U of R. Defined in an open set U of R to the N. Good. For each vector P in U, UP from J sub P to U will denote the unique solution. Okay, to the IVP 2A. Remember 2A? If you don't remember, let me write it here. 2A was dx over dt is f of x, the autonomous system, and x at 0 is nothing but p. Okay, so UP is the unique solution of this IVP. Will denote the unique solution to the IVP 2A defined on this maximal interval of existence JP, defined on a maximal interval of existence J sub P, which contains of course 0, this initial time, which contains 0, the initial time. Now define calligraphic D to be this collection of ordered pairs from R cross U such that T is in this maximal interval of existence. Okay. This is the flow domain. As also discussed earlier, now we have a proposition, our first proposition for lecture 3, which states that the set D defined in 5 is an open subset of R cross U. Okay, this is what we need to prove first. Okay, here goes the proof. Let us choose T1 comma P1 in the domain D. We show that there exists a number, positive real number. There exists delta 1 positive and an open ball B, which is of radius R1 and centered at P1, satisfying T1 minus delta 1 comma T1 plus delta 1 cross B is contained in this calligraphic D, this set. That will prove that D is indeed open in R cross U. Okay. Good. So this is what we need to show. Okay. Let me erase everything here. So since T1 comma P1 is in this set D, according to the hypothesis, there exists an integral curve U sub P1 from a maximal interval of existence J sub P1 to big U, which solves the following IVP. Solves the IVP dx over dt is equal to f of x, and x at 0 is equal to P1. This is equation number 7. Okay. It follows from the definition of the domain D. Okay. Furthermore, we also know from the definition of D that this T1 must be in this maximal interval of existence, right? So we'll first assume that T1 is positive. Okay, T1 negative can be done analogously. Okay, then if this is the case, if T1 is positive, then UP1 is of course defined, then U sub P1 is defined on this closed interval, right? Good. Since 0 is contained in JP1 and T1 is contained in JP1, therefore this closed interval has to be in JP1. Is contained in JP1 and and UP1 is of course defined on this closed interval. Now, since this is the case, one can find a sequence of real numbers T sub m such that one can always find such a sequence, right? Such that the limit of this sequence is T1, this right endpoint of this closed interval. And since UP1 is defined, U sub P1 is defined on J sub P1, U sub P1 is defined in J sub P1, and T1 is in J sub P1, there must exist Q in this open set U such that U sub P1 at time T1 is going to be Q. Okay. Additionally, since U sub P1 from J sub P1 to big U is continuous, one must have the limit of this expression of UP1 evaluated at Tm to approach UP1 at T1 equal to Q. Okay, now hence by extensibility lemma that we stated earlier in this lecture, by extensibility lemma, hence by extensibility lemma stated earlier in this lecture, we conclude that UP1, U sub P1 is also defined on this closed interval for some positive delta 1. Okay. Now we use the continuous dependence, the continuous dependence on initial conditions theorem, which was stated earlier as well, to conclude that there exists. So use continuous dependence on initial conditions theorem to state that there exists a positive number R1 such that whenever P minus the norm of P minus P1 is bounded by R1, we have that the solution of the following IVP is defined on this closed interval. So we successively use extensibility lemma and the theorem on continuous dependence on initial conditions to get here. Okay. Now we set the open ball B to be the one of radius R1 and centered at P1. Okay. One can take delta 1 positive to be small enough so that T1 minus delta 1 is positive. Okay. So one can always do that. So, well, if such a delta 1 exists according to what we have done so far, then we can always take a smaller delta 1 to serve our purpose, okay? And we do so in order to have T1 minus delta 1 to be positive. And if this is the case, T1 minus delta 1 is positive, and this open interval T1 minus delta 1 to T1 plus delta 1 is contained in 0 to T1 plus delta 1 in this closed interval, and this guy, according to what we have done so far, is contained in J sub P. Okay. Well, so what we are saying is that we can always choose a delta 1, a positive delta 1, such that this guy is contained in J sub P. Hence, if this guy T comma P is contained, this is the hypothesis, okay, in this open interval times the open ball. Okay, so if T comma P if T comma P belongs to this set, then UP, which is a map from J sub P to big U, is defined, right? This is what we have seen so far, is defined so that T also belongs to J sub P, and consequently, so if this is the situation, then T also belongs to J sub P, and consequently T comma P also belongs to D according to the definition of this calligraphic D, the domain of the flow map. So what we have done, what we have proved that if T comma P is in this set T1 minus delta 1, comma T1 plus delta 1 times B, then we also find that T comma P is in this set calligraphic D. Hence, we have shown that T1 minus delta 1 comma T1 plus delta 1 times B is contained in this set calligraphic D. Okay, so this is the case when T1 is positive and T1 is negative, can be dealt in the same way. This is how we prove that the open set, the subset calligraphic D of R cross U is indeed an open set. QED. Okay. Okay, good. So now we define the flow map of a vector field. Definition: flow map of a vector field Okay, I think I'll take a break here and I'll get back to the definition of flow map of a vector field in the second lecture. Thank you very much for attending the first segment. Well, I'll get back to the definition of flow map of a vector field in the second segment of this third lecture. Okay, thank you for attending this the first segment.